Welcome to the last lecture of QCamp. My name is Chong. Chemistry. So right here today, I'm not going to do it, but rather I'm going to introduce you on how to apply chemistry intuitively to chemistry topics. So as you may know, in the lecture, there is no and that's because I want to talk for a more visual presentation. Actually, the chemistry in university is a very pretty advanced module, and that's because you need a lot of mathematical prerequisites. You need to understand different calculus, algebra, differential equations, and sort of vector spaces, which can be very, very complicated if you don't know what. So for today, I'm going to present. I'll bring you through what is it like to study, or how does what we are trying to say when we want to implement quantum mechanics to chemistry. We want to have a visualization of what is happening. So if you want to know more about chemistry, I have provided several references in the lecture notes to read out. So one of them is the liberal text chemistry. This is pretty good for those that have more idea of what's going on in chemistry or in the quantum mechanics. So this serves as a very useful guide. It's actually written for chemists who don't actually study physics. And then if you are the more physics adept student, you can go to hyperphysics, which will teach you everything about chemistry from the perspective of a chemist. And those who are really advanced, so in this lecture, right, I've completely taken mathematics out of it. So instead, I'll present pictures, animations, and so let us begin by thinking. Okay, so let us begin with this quantum chemistry. Yeah, in the past 4 days, you've been learning about the qubit. Right? The qubit is basically a quantum object that has two energy states. Right? But in this lecture, I'm going to talk about these three things, right? The electron, the atom, and the molecule that serves the foundation for chemistry. So let's begin pretty simple, right? The qubit, right? You've learned this, two quantum states for qubit, and then this is how you write the wave function of the qubit. You have these two states, and then these are the entities, right? This can be complex numbers. But why stop at two? Okay, when you can have n quantum states, right? So I place this quantum state on the 0, 9. So this object is basically a one-dimensional object. And I can describe this quantum object by taking the same linear combination of all these states in this ordering. Now, to generalize this, why stop at one dimension? Then we can have 3 dimensions, right? So this quantum object is basically a linear combination of all of these quantum states here, right? So we have n to the power of 3 quantum states, n meaning the number of states in one dimension, right? And then this n to the power of 3 is just a sum of the total number of quantum states in this tree here. So essentially, if we were to generalize this all infinite states, meaning every single is a quantum state, then is basically a description of an electron. The electron is basically a 3D quantum object where every single point in space is a quantum state, right? So the superposition, right, of all these position states in this space. And instead of a summation, we have an integral because it's now a continuous summation. Okay. So it's not a discrete summation like we did it in qubits or in discrete space. Now it's a continuum space. So that is the electron, right? And the electron is the foundation chemistry. It's a useful object, right? That we can use it to describe nature. And it's so useful that we can almost call it real. And this is the quote by Richard Point. So let us study how does the electron behave. So I think on Wednesday we have been introduced to this Schrödinger equation. It's basically telling you how this electron behaves or how this quantum object behaves. So the equation basically, right, how the electron behaves is when you apply the energy operator onto the state, right? It creates a change in the wave function, right? This is a change in the wave function, and that's how the electron changes in time. That's how the electron behaves in time, right? The Hamiltonian consists of two parts. One is a kinetic energy, the other is the actual energy. Okay. So I'm not sure if you have studied this on Wednesday. Can anyone tell me why is there a H bar over here? Because Einstein actually explained something called the Schrödinger photoelectric effect. So you know, right, from the this photoelectric effect, when there's a photon striking the metal surface, it actually have this right frequency. Okay? Right. Just at the right frequency, you emit an electron out. And that is the photoelectric effect. And this equation, the minimum frequency is given by this effect, right? Where this energy is the difference in the energy difference between the these two energy levels of the electron. So this one is the difference, and that is why you get the Planck constant here. But you see, right, there is this H and the H bar. So H bar is actually H over 2 pi, right? Anyone tell me why you need to do this? Divided by H bar. Anyone know? I give you a hint, it's something to do with circles. Okay, the reason is because 2 pi represents 1 unit of oscillation. Right. So what we are doing here is we are counting units of oscillation, the number of oscillations, the number of cycles in the wave function. That is why we need to divide by 2 pi just to get that unit out. Okay, so now enough talk about mathematics. Let us look, see some action. So let us look at the behavior of 1D free electron. These are the energy terms, right? This is a kinetic energy, and because it's free, there is no potential energy bounding the electron. So how does the electron looks like? In this case, the electron looks like a wave, yeah, right? This is the real part of the wave function, and then this is the imaginary part of the wave function. If you do a modulus square of the wave function, it gives you the probability density of finding the electron at a certain position. So one thing to notice here is that as the electron moves across from the left to the right, the wave function actually spreads out. Right? And that is because the electron has a superposition of multiple moments, multiple velocities. So some are moving slower, some are moving faster. So that's why the wave function actually spreads out. And because it spreads out, right, over a larger area, the normalization has to be preserved. And that's why the amplitude preserves. Okay, so this is the effect, right? This is what you're seeing here. So why stop at 1D? We can have 2. Right? It's a two-dimensional representation of the electron. And from here, you can actually imagine how that three-dimensional actual electron looks like. So imagine like a ball, but it looks like this, or space in between. And then if you do a modular square, right, it looks like a fuzzy ball that's traveling across. Right, so this is how the electron looks like in free space. Now, to make it more interesting, I'm going to put a barrier here. I call this the energy barrier or the potential barrier, where the electron will experience a potential only at this spot. Whereas this position and this position, before and after, there is no potential. Okay. So to make this simple, we're gonna look at the electron probability density. So I'm going to set this wave, this electron be crashing into this potential barrier. Guess what happens? So let us look at the first case, the simplest case. Right? So if the kinetic energy is actually much smaller than the potential energy barrier, you'll see basically the electron just bounce off on the wall of the barrier. Nothing too interesting. But what is interesting here is that you see this fringes here. Can anyone tell me why you see fringes here? The wave function of the incoming wave is interfering with the reflected wave constructively and destructively. That is why you see those fringes here. Okay? So basically, the electron is interfering with itself constructively and destructively, and that's why you see those fringes here. Now, what happens if I increase the kinetic energy? What happens here is that the electron, part of the electron gets transmitted, and part of the electron gets reflected. Okay, this is called quantum tunneling. So there's only one electron here, but part of it gets transmitted. So there's a 50% chance of finding an electron either on the other side of the barrier or on the other side of the barrier. Okay? There's only one electron here. So if you measure right here, right, the electron can be here, here, or here. Okay? So this is quantum tunneling. But what if I increase the kinetic energy even further? Okay. Basically, the whole electron gets transmitted through the barrier. So in summary, the electron is just a 3D quantum object. Okay. I put a star because of partial description. You will know why later. And the electron can actually quantum tunnel through any non-infinite peak. Non-infinite basically meaning that the potential is not an infinite variable, that the electron cannot pass through. So any finite peak barrier, there's a chance that the electron can actually quantum tunnel through. So with this electron out of the way, I can move on to the atom. Okay, understand the hydrogen atom. Understand. So if you understand this, I think you'll be able to, well, basically do all the chemistry problems, I hope. Yeah. So this picture, right, is the first observation of the hydrogen atom. So this is basically the electron probability density of the hydrogen atom. So the hydrogen atom, we don't know what I'm talking about. It's basically an electron with a proton, surrounded by a proton. And the energy terms of the electron is basically the kinetic, and then the potential, the Coulomb potential energy. It's basically the interaction between the electron and the proton. Okay, so I'm going to introduce you the wave function, and it is called the atomic orbitals. In the ground state of the hydrogen atom, meaning the hydrogen atom at 0 Kelvin, the lowest energy possible. The wave function looks like this. This is the probability density. Of course, we cannot observe the wave function directly, so you just have to settle for the probability. Now, if you pump in more energy into the hydrogen, what happens is that the wave function gets bigger, and you will see something. There are gaps in the probability density. Right? So these darker areas means that there is low probability of finding the electron, and we call this orbital nodes. Right? You may be wondering why is there orbital nodes, right? And then why the shape is getting bigger and bigger, and we have more and more gaps in free as the energy of the atom gets bigger. But before that, I'm gonna tell you why or what is the atomic orbital. They are basically the energy levels of the atom. Right? They are eigenstates of the Hamiltonian or the energy operator of the electron in the atom. Right? And the associated energies are called the orbital energies or the eigenenergies of the Hamiltonian. And this too is related in this eigenvalue equation. Right? It's called the time-independent Schrödinger equation. Okay, so this is where you get the eigenstates and eigenenergy. In chemistry, it is called the atomic orbitals. So what are atomic orbitals? What do they actually mean, basically? It actually means that the wave function or the probability wave function is it does not change in time, right? It has a constant energy and is analog to a standing wave in classical mechanics. So you see the wave, right? Although it's switching, but it does not travel across the medium. In this case, it is standing. It is not moving in the sense that it's translating across the space. So in quantum mechanics, right, if we have states, these two eigenstates, right, the wave function might be changing in time, but the probability density remains fixed, right, with an associated. And same goes for the other eigenstates as well. This is what we mean by stationary states. If we were to superpose these two eigenstates, right, we have the wave function that is changing, right? The probability density changes. So this one is no longer a stationary state. And then the energy, right, oscillates between these two. So this is what we meant. So these two are atomic. In this case, we can think of it as eigenstates. For an atom, this will be the atomic orbitals. So the eigen energies, the orbital energies, they are also the energy levels of the atom that you have learned in chemistry or in physics. They are basically the same. Okay. So you have seen this spectrum, right? Depending on where the originally had can excite or de-excite, right? Giving out light or absorbing photons of light. So in this case, this is the emission spectrum of hydrogen. You will see 4 lines here that is correspond to this series. Okay. So you can also take advantage of this to create your lasers, simulated emission, introduced, I think, by Alex in the first lecture. So these energy levels, right? They are basically the orbital energies of the atom. In this case, is some other atom, not a different atom. Okay, you can use whatever atoms you like to create whatever lasers. Okay, so you may be wondering why are there orbital nodes that I saw in the slide just. Anyone tell me why is there orbital nodes? Right. So suppose your electron wave function, right, is like this. Of course, it's not normalized. We can think of it as a wave, so I use a sine wave as a number. And if I were to, and the thing that I notice is that it always goes between positive and negative. At some point in space, there's always this crossing, right, where the amplitude is going to be 0. Okay. When you do a modular square, all the signs all become positive, right? You flag up above, right? But then the points at which it crosses the x-axis remains there, and this is where you see the nodes. So, for example, let us look at the atomic orbitals. This is we are looking at the radial part of the wave function. So we are looking at the radius, the radial axis. So this is the wave function. Actually start off intersect at 0 at 2, and then it goes down exponentially all the way to all the way, right? And this is the radial wave function. What happens if you do a modulus square? So this is the probability density. You'll be wondering why is there R squared here? And that's because it is calculating the probability of the surface area of the sphere in this diagram. So you need to put an R squared to account for the surface area. Of course, there is a 4 pi over there, but this is just a numerical factor. You can just put it into the plot. Okay, so in the ground state, there is no nodes. That's why you didn't see any gaps in between. Right? But if I were to excite, you will see a crossing here. Okay, and this is the node. If I were to do a modulus square again, this is the node here. This is why you see there is you will not be able to find an electron right here. So in general, if you pump in more and more energy, this is what you see, right? The orbitals, they get bigger, and then you see more and more nodes. Right? The higher the orbital energy, the more nodes it has, the bigger it becomes. Okay? So this is just a part of the this atomic orbitals. It's just a spherical shape, but in fact, it can take on many different shapes, right? And we have the sphere, which is we call the s orbital, right? And then we have the p orbital, and different, two balls and different axes. And then we have d orbitals, right? Balls at different x4, and then we have the f orbitals. These are all the eigenstates of the hydrogen atom. Okay, from the lowest to the highest orbital energy. And then these are all the different kinds of orbitals. So if you combine everything together, right, you'll get something like this. Right. So this is these are all the different eigenstates of the atomic orbital. The dots don't represent the electron, rather the concentration of the points of the dots represent the probability density of finding the electron. Okay. Cool, right? Looks very awesome. Yeah, so that brings us to the end of this section of atoms. Atomic orbitals are basically eigenstates with only one electron. Okay. The bigger and the higher energy they are, the more node it has. So one joke about atom is I try to stay positive, but it's rather fun so much negative. Okay, so let us move on to something that we have studied in the past 3 or 4 years, talking about electron spin. I want to emphasize this more. So let us look at what the video on this.
Best observed, the modern version of the Stern-Gerlach experiment used silver atoms. Here we use magnets and electrons directly. The device has a north and south pole shaped to create a magnetic field that is stronger near the tip. This varies the force on charged particles passing through. The magnet is sent through with the north pole up and south pole down. The magnetic field creates a force that deflects the magnet upward as it passes through the field. As we change the orientation of the magnets being sent through, we see the change in the amount and direction of the deflections. Deflections depend on the orientation. This is as expected. When electrons are sent through the field, they too are deflected. But they always arrive at the screen deflected either up or down, never in between, like the magnets. Each electron behaves as a magnet, but with only one of two possible orientations, up or down. This intrinsic property of an electron called spin.
All right, so spin is an intrinsic property of electron. It's not saying that the electron is spinning, but rather the property that actually reflects up or down in this case, right? In the actual experiment, right, we actually use silver atoms, hot silver atoms, and it's not the metal. It's actually a acid gas. We send it through this big magnet here, and then we see a deflection over here. So why we use silver atoms is because if you draw the reverse diagram and multiply across thing, right, we see that there is this valence, this single valence electron at the outermost shell. Right, this is what that is causing the this effect that we are seeing here. All the other electrons here, they don't contribute to the this result, and that is because the spins cancel out, and only the resultant spin is due to this electron. So it's doing there's doing this. So to emphasize, right, this electron actually behaves like tiny magnets, and this is where magnets originates from, due to all these electrons, right? So we have, if we look at this simple analogy, right, a bar magnet, if we align low energy, and then if we end up aligning with high energy, here is a current loop, but we use the right-hand grip rule to determine the direction of the magnetic field, induced magnetic field. And then for the electrons, which is this one, right, when it's spin down, right, it actually has low energy, right? If it's spin up, it's actually a high energy. Okay, it's like a qubit. Basically, the electron behaves like a qubit. So in an atom, the full description is this. Right, the 3D quantum object is spin. So not only have atomic orbitals, we have the spin component as well. And we use a connector or tensor product to combine these two different properties together. And that is the full wave function of an electron in an atom. Okay. Right. So that's it. That's a summary of the electron spin. Electron behaves like tiny magnets, and then they are 3D quantum objects with spin. So you can take this down. I'm so happy that you are copying this down, because last year no one did it. Right. Okay, so if I continue, right, I'm going to talk about two electrons. Previously, all we have in this something is just one electron. Now, when we bring in one more electron, things change, right? I want to talk about this or discuss about this idea when you have two electrons, and it is to do with the fact that the two electrons can never be in the same quantum state, and because of that, it gives rise to all the phenomena that you know today, like we don't actually quantum tunnel through our friends, you know, we can't do this, you know, like face my hand through this. It also explains why we are so powerful, right? Why we can feel what we can. And it's to do with the fact that electrons don't like to share state with each other, either in the same state. So I want to begin this concept or this this phenomenon by starting off simple. I want to look at balls, right? how to distinguish objects. So look at this picture. Can anyone tell me how do you differentiate in all the different balls? And any differentiating factors there that you can tell apart different balls? Color, right? Texture, size. So we can distinguish objects by looking at the physical appearance of the object, by differentiating based on the physical quantities of the attributes. Now, what if I give you an identical object? Right? How do we distinguish them? When I say identical, I mean that if it looks the same, it swings like the dart, means it behaves the same way, and then it cracks like a dart. So that's what I meant by identical. They behave and looks the same way. Right? So how do we distinguish them? Any ideas? How do we tell apart from this ball and this ball?
You can use a marker.
I use a marker position, right? So if I have different balls that are running around, I can actually say measure the position and the momentum of the object, tell apart from other objects. So for example, I can track this ball that's moving slowly. So if I don't lose sight of it, I actually be able to distinguish this ball from the other, from the others. So that's what we meant by distinguish identical objects. What happens if we were to distinguish two electrons? Right? The electrons are all identical. They have the same charge, same mass, right? Same behavior, they tell each other, right? How do we distinguish them? So suppose where we have both electrons colliding with each other with equal speed, right? Let's say we have a small momentum, right? And then we look at the probability density of finding any electron. Of course, this is pretty predictable, right? Two electrons approach each other, right? And then they interfere, but then they repel each other, right? So we can actually track, right, the electron from start to finish. So we can actually distinguish them, right? But there are some interference here. But what happens if we have a larger speed, a larger momentum? And that's what happens when you have and this is what happens, right? They interfere so much that their wave function actually interferes with each other. And from here, you are unable to distinguish these two electrons. So for example, if I track this electron, and then when they merge, what happens? Is this electron here or then? Same for the other electron. Right. So this is a this gives rise to a concept, right, in particles. But we meant by distinguished particles, when we cannot distinguish particles, we meant that we exchanging two particles don't change probability density. Okay, this means that if we have a probability density like this, that is denoted by R1 and R2, we swap them, it remains unchanged. Makes sense, right? When we swap these two particles, it does not change anything because they're both identical, indistinguishable. Okay. Now, what this means that the wave function. Now, if we remove the modular square, right, the wave function must satisfy this. Right? When we swap the conditions, right, the resultant wave function is either the same or the negative of the wave function. Because when you modular square, you get back the same probability density, whether you have a change. And this is true for all of the particles here. If I swap any of these particles, the wave function or the probability density will remain changed. So examples of this. If the sign is positive, an example of this will be photons light. If it's minus, the particles will be electrons or protons in this case. Okay. So let us look at some concrete examples. If we were to look at the probability density, a beam. Right? And I'm gonna tell you, I'm gonna plot the Pauli density. Here, the first axis will be the first particle position. The second axis will be the second particle position. So it's different from the earlier case where we plot them on the same space. Now it's two different spaces. So if you look at the photons, right? If they are always along this diagonal, meaning that they are always at the same space. So this phenomenon is considering photons like to cluster, they like to be with each other in the same state. Okay. But for electrons that has the same spin, don't like to cluster, right? They always avoid each other. So let's say one electron is here, the other electron will be here. The other electron will be will be a different space. So for example, point 2, the first electron, the other electron will be at some other space. They will never be at the same spot. Okay. So this phenomenon is called the Pauli exclusion principle. I think you heard this before in your chemistry lessons, right? No electron can occupy the same quantum states simultaneously. And yet, it has nothing to do with the repulsion or Coulomb repulsion of the electrons. It has nothing to do with like charges repelling each other. If the electrons have different spin, they like to cluster, right? They like to be with each other. Right? If it's the same spin, they don't like to cluster. So we in the earlier examples we just saw, they don't like to cluster. But you may be wondering, photons, they actually cluster, do they? Right, so this brings us, we're gonna diverge away from chemistry a bit and look at thoughts. So we're gonna look at, we're gonna diverge a bit and look at photons actually cluster. Now we just saw how electrons actually no. Yeah. Okay, so we're gonna diverge a bit and look at photon cluster because I received feedback from last year that is there any examples of how photons actually cluster? And this is a very one of the more exciting part in physics we do with photonics. So yeah.
This is a 50-50 beam splitter. When 2 photons enter, there are 4 possible outcomes. 1. 2 photons enter and both exit on the left-hand side. 2. The photons enter and both exit on the right-hand side. 3. Both photons exit on the same side at which they entered. 4. Both photons cross over to the opposite side to the one at which they entered. In general, the state at the output of the beam splitter will be a superposition with contributions from each of these 4 options. The contribution to the final state from both photons crossing to the opposite side of the beam splitter has opposite sign to the contribution from both photons staying on the same side. If the 2 photons have identical wave packet shapes so that they are indistinguishable from each other, then the contributions have exactly equal amplitude. However, because they have opposite sign, they cancel out. So, the 2 parts which could result in 1 photon exiting on each side destructively interfere. This means that both photons must exit on either the left or the right-hand side. This remarkable and important quantum interference effect is known as the Hongo-Mandel effect.
So for photons, they actually cluster. For electrons, they don't, if they are the same spin. Right. So in summary, right? This is what we talk about. Photons cluster in interference, and it's called the Hongo-Mandel effect. Cluster they interfere in the same state, right? It's called the Pauli exclusion principle. Okay. So one joke is that if an atom lost an electron, they should really keep an eye on it. Right? So so this Pauli exclusion principle is pretty important because it serves the foundation of many chemistry concepts. We'll learn how to use this Pauli exclusion principle to build up atoms on how different electrons in an atom behave. Okay. So I'm gonna talk about the atoms, right? In particular, I'm gonna talk about all these elements. Of course, when you talk about these elements, you have more electrons, not just one. So we just talk about the hydrogen atom, the hydrogen atom is here, right? But then you have all of these atoms here. What is going on? Okay. We want to talk about the electron wave function in an atom. Same story applies. We look at the Hamiltonian, the energy of the atom. Okay, so we have the potential energy, kinetic energy, Coulomb energy, all sorts of energies, right? It's gonna be complicated. So to make this simpler, chemists have come up with a special approximation. An approximation, basically, one electron occupies one atomic molecule using with different spins, using the Pauli exclusion principle as the fundamental rule. Okay. So what this means is that the wave function of electrons in the atom, right, is a Kronecker product of all the occupied atomic orbitals. So, for example, let's say if you have a two-electron system in the atom. So I'm going to follow this. So I'm just going to look at this one, 1s, 1s, and then all the other orbitals, they are all empty. So what is the wave function going to look like? Right, the wave function will approximation, and then this is the normalization. Like that. 1s spin up on the first electron, and then Kronecker product with the second electron. Okay. But because we have just learned that the wave function must be a negative, must be anti-symmetric, so that the overall population is the same, you need to take a negative of the negative. So when you solve this two, you give us the negative of it. So answer for that one is spin down. So this is one example. So you can imagine if there are 3 or more electrons, the wave function over there is going to be very complicated. So this is just a simple example for 2 electrons. Okay. So in chemistry, if you ever gone study in chemistry, you will learn how to fill this up with not only just exclusion principle, but different kind of rules as well. Okay. You're going to learn about our valve principle, where you have the orbitals in a very systematic way. Okay. So we have 1s, 2s, and then 2p, 3s, 3p, 4s, and so on and so forth. Yeah, so in chemistry, you're going to learn about Hund's rule. Basically, all the orbitals must be filled singly before we fill them doubly. Okay. And the valence and the last electron that fills up will determine where you put the element. So for hydrogen, it's 1s, then helium, then lithium. Lithium has 3 electrons, so it should fill up the 2s. When the last electron fill up the 2s, then where it is. Yes. Then 2p, 3s, 3p, so on and so forth. Right. So this is how the elements are arranged on the periodic table. So you see this only group is the f orbitals. So in summary, bigger atoms, the wave function it's pretty difficult to solve, and we approximate them using that sort of formula, right? Optimize the atomic orbitals, and the elements in the periodic table are arranged based on the last few orbitals. So this is how chemists actually solves approximate bigger atoms. Any questions? So now we're going to talk about molecules. We have been talking about atoms, right? Now we're going to look at how atoms come together and form molecules. So life is a relationship between molecules. They are all made up of molecules. So we have old MacDonald, cow, turkey, giraffe, duck, serpent, and goose. So these are all real molecules, I believe. If you can ever synthesize them. Yeah. So this is Linus Pauling. It's a legendary the one that actually applies from mechanics to chemistry. All right, so I'm going to talk about simple molecules. Right? We are going to look at the hydrogen molecule. Simple, right? Just two hydrogen atoms comes together and form the hydrogen bond. So I was about to make a joke about sodium and hydrogen. So, in a similar fashion of bonding orbitals, we have molecular orbitals. Basically, it's a linear combination of atomic orbitals, meaning that you add these two atomic orbitals as they come together. So this is what chemists actually define the states of the molecules. And this basically explains or is a part of the explanation of how molecules form. Right? This forms a stable wave function for the atom, for the molecule, and that's how the molecules can stay at the molecule. Right? They don't split apart unless you put enough energy to make them split apart. And then that's how they form waves. Okay. So an animation, right? Very cool animations. You have these two atoms that comes together, and then as the atoms at the wave function actually interfere, they form a bond. But if they're in the low enough energy. If you have high enough energy, then you'll see a separation like this. We call this an anti-bonding. So if you measure the energy of this, you look at this. Right, there is this dip in this case for the bonding orbital, right? And as they are become far apart, there is no energy between them, so they come to. But anti-bonding orbital, it is always positive, right? So the molecule will not be stable. So this is just two of the eigenstates. But in fact, there are more eigenstates, right? So how to get all these eigenstates is by solving the time independent dynamic of the molecule. Okay, and this next animation will show you all the different kinds of eigenstates that we can have for diatomic molecules. This is a diatomic molecule. This is the potential. Yeah, so these are all the different eigenstates of the diatomic molecule. So this what we are saying here is the property density ratio. So associated with the energy, energy. Some of the eigenenergies are the same, right? So we call it determinant. Yeah, so you can actually solve this one equation using computer simulation. So you don't like that button, which is pretty simple. So as you notice, right, atoms don't actually come together and collide. They are all actually at a distance. So this is one joke about
You know that atoms never touch each other. And since we're made of atoms, we've never touched anything in our entire lives. So to answer your question, officer, no, I did not punch that kid.
yeah, so this will be this guy. Okay, so if you understand this, right, you can actually do interesting, visualize interesting stuff. In chemistry, we do a lot of chemical reactions. And if you look at the wave function of this molecule during the reactions, you'll see something very, very cool. So basically, in this electron transfer, the electron moves from one molecule to the other molecule. But what happens is that the wave function actually changes. The wave function of the molecule actually changes. And then this one is that hydrogen atom transfer, means the electron and a proton actually transfer from one side. So in summary, molecular orbitals that we just discussed are basically just linear commutator. And it serves as a foundation for the molecular bond. And basically and how you get the molecular orbitals exactly is by solving the the time-independent Schrödinger equation. So one example here is that two atoms bonding. So we call this, so you see the wave function actually extends on these both sides of the electron. And we call them the pi bond. Yeah, so it's not just a single block, but it's rather a complicated block, depending on how the atomic orbitals look like. So advanced core chemistry show about the reaction. So I hope I understood it. Yeah. Okay, so with that, quantum mechanics I've explained all of the chemistry and most of the physics. So you have seen an electron that can quantum tunnel, and you've seen how atoms look like, and then how molecules form. Right? With that, I shall conclude. And that is how the atoms or molecules are formed. Right? It's formed. Right? It's right. So thank you very much for listening to my lecture.